everyone, this is Dr. Sirisha, working as Associate Professor in Institute of Aeronautical Engineering College. Today we are going to learn about the basic definitions and or basic terms which we use in linear data structures. That is the well-known and the famous stacks and queues, the various types of queues and how we work with them. Let's begin our journey with a stack. What is a stack? Stack is a linear data structure where the constraint is in such a way that you are allowed to insert an element or remove an element only at one end. The other end is sealed for any further operations. So have a look at the picture which I have given. Top is the variable which is going to help you out to navigate through the stack, and top will always be pointing to the most recently inserted element. So it is also known as last in first out, right? The element which enters the stack first will be going out of the stack first. Such is the nature of a stack. Initially, as the stack is empty, the top will be holding -1, just specifying that the stack is empty. Well and good. What if I insert few elements into it? Have a look at this one. I have inserted 3 elements. The insert operation in stack is known as push operation. Okay, I pushed 3 elements into the stack. Once I push 3, the top gets incremented and it is pointing to an index value 2. That is the topmost element, 21. Such is the job of a stack. So the elements in the reverse order of the order in which they are inserted into the stack are excluded from the stack. Okay, right. So what are the basic operations that we are going to perform on a stack? One is the push operation, which is inserting an element. The other is pop operation, which is removing an element from the stack. Then peek. Peek is nothing but looking at the top element on the stack. There is one point which you need to understand, guys. When we work with stacks, we have access rights on the element pointed by top. That is, either you can pop the element pointed by top, or you can push an element on head of that. We do not have access rights to the elements which are below the top, right? So if you want to check what is the element on the top, peek is the right operation. It returns the element which is pointed by the top. Okay. The next 2 operations are isFull and isEmpty. isFull is an operation which is going to help you out to check whether the stack is full or not. What do you mean by full? That is a good question. So if the size of a stack is say n, okay, so what if you are trying to push an n+1th item into it? So if the capacity of a bag is 10 kgs, if you try to put 1 more kg into it, is it going to accept? It is not going to. Similarly, if the stack size is n and if you are trying to insert 1 more element into it, then it is going to, this function will help you to tell you that overflow condition has occurred. Overflow. If you try to insert 1 more element, it is going to overflow. That means even if you insert, it will not be considered, right? You have exceeded the capacity. So if isFull function is true, means overflow condition has occurred. A contrary to that is isEmpty. What it is helpful in pop operations. Popping is nothing but removing an element, deleting an element from a stack. What is the point in removing an element from an empty stack, right? So is there any point removing something out of an empty bag? We are not magicians to bring out a rabbit or a cat, right? So removing something out of an empty bag is of no point. Similarly, if a stack is empty and if you are still trying to perform pop operation, isEmpty is a function which is going to help you out. If this isEmpty function is true, then we call that underflow condition has occurred. Okay, so these are the two functions which will help you in push and pop functions respectively. Okay, these are the basic terms which we are going to use. Right. So let's look at the operations of a stack. So initially when the stack is empty, the top is pointing to -1. If I push a value into it, the top will be incremented to index value 0 and the element is inserted. So the peak element is 21. Next, if I insert 15, that is I push 15, top is further incremented to index value 1 and now the peak element is 15. So what if I insert 4 elements, 13, 24, 11 and 35 respectively? Then the top will be pointing to the most recently inserted element, which is 35, and the peak element is also 35. That's what I was trying to tell you guys. We have access only to the top element. We cannot touch these elements from index values 0 to 4. We don't have the access rights, right? What will happen if you try to push one more element? You can see that top is pointing to the element with the highest index value, right, which is 5. The total capacity of the stack is 6. So the index values run from 0 to 5. Now top is pointing to the 5th index, right? Now if you try to insert one more element, overflow condition raises, saying that you cannot, right? So next, let's look at the underflow condition, how it works. So if you try to pop an element here, simply remove the element, have to remove, decrement the top. Once you decrement the top is pointing to the element 11, which is at index value 4, and the peak element is also 11 now. So it literally says you that you have deleted 35. It is no longer under consideration. Okay, so what if you perform the same pop operation 4 times? So it will lead to removing the elements at index value 4, 3, 2 and 1. Right? Now the top is pointing to 21, which is at index value 0. Even the peak element is 21 now. Okay. What if I try to remove the element in a stack? And the only element in the stack, if I say clearly. So if I remove the only element present in the stack becomes empty. So when a stack becomes empty, the top will come to its default value, which is -1, right? What if I try to again pop? So it will tell that underflow condition has occurred. Very good, right? So you're trying to remove an element from an empty stack. With this, I can conclude that if top is holding a value n-1, where n is the total capacity of the stack, and if I try to perform a push operation, then it will give me overflow, right? And if my top is having a value -1, and if I try to perform pop operation, it will show underflow, right? These two are very important points. Remember these definitions and these terminologies: push, pop, overflow and underflow. Very good. Right. Then what are the basic applications of stack? Where it is used? The applications are in the basic arithmetic logic unit, ALU, where all the operations, expressions are evaluated. There stacks will be used. So we are going to feed our arithmetic logic unit with an infix expression, which will be converted into postfix, and this postfix will be evaluated and the result is pushed back. So while converting an infix to postfix, stacks will be used as an intermediate agent. From evaluating postfix expression also we use stack as an intermediate agent. Right? So this is how arithmetic logic units use stacks. Next is backtracking. Backtracking. So in your say recursion where a function call itself, right? So in those cases, we need to, whenever a function call raises and the function definition is done, we need to go back to the place where the function is actually called. So the return addresses are stored in stack. Next is delimited checking, which is nothing but parenthesis balancing. Have a look at this one. If you are working with C or C++ or Java, you'll be using flat brackets to represent compound statements, right? So, for example, let this be the structure. Stacks will be used to check whether it is balanced or not. Every open parenthesis is inserted into the stack. Whenever you encounter a closed parenthesis, remove an open parenthesis in your stack. So once compilation is done, if the stack is again empty, that means you have started with an empty stack, and if you end with an empty stack, then it is a balanced one or else not. Okay, so the next application is reverse data. So if the elements are 1, 2, 3 and 4, I insert them into the stack 1, 2, 3 and 4. Now I pop them out to display. So 4, then next pop is 3, next pop is 2, next pop is 1. Can you see I have reversed the data, right? To reverse the data, simple technique is to use a stack. Push them, then pop them out, right? Then processing of function calls, which is similar to your recursion. When we call a function, right? When I call a function from another function, say function 1 is trying to call function 2. So whenever the working of function 2 is done, it is supposed to track back to the place where it is being called, right? So whenever function 1 leaves its control and goes to function 2, it stores the address. For this purpose, we use stacks. So these are the basic applications of stacks. The next linear structure is queue. So what is a queue? It is a linear data structure where the order is in such a way that the first inserted element will be removed first, right? That is first in, first out. So it will be having two ends, my dear. Okay, so front end and rear end. Say 1, 2, 3, 4 are the elements. We insert the elements at the rear end. We delete the elements from the front end. Okay, so these are the list of operations which we are going to perform on queues. So insertion in a queue is known as enqueue. Deletion is dequeue. So, and specifically guys, in a linear queue, we have to insert from the rear end, remove at the front end. Okay, that means the direction from which you are going to work on a queue are predefined. Okay, very good. Next is full, to check whether a queue is full or not, right? So the same conditions which we have seen in stacks, overflow and underflow. To enqueue, I take the help of is full. To dequeue, I take the help of is empty. To check whether the queue is full or not, and to check whether the queue is empty or not, respectively, right? When working with stacks, we had the variable top, which used to point the most recently inserted element. Here we have two pointers. One is front and rear, right? So whenever I want to look at the elements that are present at the front end and rear end, I'm going to use these two functions, front and rear, just to get the element at the front and to get the element at the rear respectively. Okay, so these are the say 6 primary functions which I'm going to use on a linear queue. So have a look at these two contrasting data structures, stacks versus queues. Let's please keep one point in mind. Never ever judge them. Stack is wonderful and versatile in its own nature, whereas queue is beautiful in its own nature. Right? So for parenthesis balancing, don't even think of queues. For evaluation of any expression, don't even think of queues. They are not good at. Okay, so whenever comes to a few applications like using a buffer, don't even think of stacks. Queues are the best. Memory management, don't think of stacks. Only queues work. So these two are linear data structures meant or designed exclusively for queue purpose. So we cannot judge which one is good. They both are designed for two different purposes. They are two sides of the coin. Who can say that which side of the coin will give you a penny more, right? No. If you take a penny and you look at its head, do you think showing the head to a person is he going to give you a extra penny, or is going to take an under penny from you? No, right? Even if you show the tail, the story is the same. The same point. These two data structures are designed for two different purposes. So never ever compare. So I literally say that comparing these two things itself is an absurd. Right? Because many students ask me, ma'am, which one is beneficial? So that question itself is wrong. Right. Now, let's look at the operations of queues. Right? Initially, the front and rear will be holding -1. The default values of front and rear when the queue is empty. Very good. Next, when I insert or enqueue the first element, which is 6, as it is the first element into my queue, I'm going to increment both front and rear. I'll increment them both. Right? Now, if I enqueue 15, right, as the queue is not empty anymore, I'll just increment rear and insert. If I again perform enqueue of 21, I'll just increment rear and insert. What if I enqueue 11? So increment rear and insert. Enqueue 7, increment rear and insert. Next, enqueue 14, increment rear and insert. If I try to enqueue 2 now, have a look at this picture, my dears. The limit is 6 elements. The size of the queue is 6, where the index values run from 0 to 5. And now you can see that with an incremental stage, I have inserted one by one element. Thereby, my rear is pointing to the highest index value now. It is pointing to the index value 5. Right? So, if I try to insert, it will say that it's an overflow condition. You are trying to insert an element into a queue which is already full. Why? Because the rear is pointing to the highest index value. Okay? This is overflow condition, my dears. What if I dequeue? Remove the element from the front. Just increment the front. Job done. Again a dequeue. Now the front will be pointing to 21. Again a dequeue. It will be pointing to 11. Again a dequeue. It will point to 7. Again a dequeue. It will point to 14. Again a dequeue. What it will do, as the front and rear are pointing to the only element in your queue, both will get their default values, which is -1, after removing the only element present in your queue. Right? So this is how the queue, linear queue operations will be done. What will happen if you try to again perform a dequeue? That means front and rear both are pointing to -1. When you try to perform a pop operation, that is dequeue operation, it will go with underflow condition, right? So let's conclude it. So if rare is holding a value n minus 1, whereas n is the total number of elements in a queue, that is the capacity of the queue, then and if you perform enqueue operation, it will raise overflow condition. And if friend is equal to minus 1, or even you can check rare is equal to minus 1, anyone is fine, right? And if you perform dequeue operation, it will go with the underflow, it will raise an underflow condition. Okay, so please do remember this one, my friends. Coming to the advantages, it's highly advantageous for handling the data of multiple data types. It's flexible and very fast, and they have infinite length compared with arrays. When you work with linked list, when you try to implement a queue using linked list, you can dynamically increase the size of queue as you wish based upon its requirement. Disadvantage, please remember this one. Have a look at this current scenario, guys. So I have inserted the elements, 6 elements. So my rare is pointing to the highest index value. Now I have dequeued 3 elements. I have removed 3 elements. Now my friend is pointing to index value 3. What will happen if I try to enqueue now? I want to enqueue 31 now. If I try to enqueue 31, it will simply say that as rare is pointing to n minus 1, overflow, I cannot take. But if you look it into the actual condition, half of your queue is empty. Half of your queue is empty. That is the major disadvantage of linear queues. It is having simply one condition saying that if the rare is pointing to the highest index value, you can conclude that the queue is full. But in actual scenario, it is not the fact, right? If you perform few dequeue operations, then you'll get a vacant place, but you cannot utilize it, right? So that is the basic drawback of linear queues. Coming to the applications. Applications of queues, where resource sharing they'll be used, right? So next is asynchronous data transfer. Simple point is, suppose a source is transferring its data to a destination. Source is very fast in sending the data, where the destination is very slow in receiving the data or processing the data. So now the destination cannot afford to lose the data because of its inefficiency or slow processing, whatever the reason it may be. So what it is going to do is, it is going to create a buffer. It is going to store the data in the cells. So as soon as the data it receives from the source, it is going to add it in the buffer, and it is going to remove the elements at the front end. So the front end will be facing towards the destination, whereas the rear end will be facing the source. So the new elements will be added at the rear end, and the first entered elements will be removed from the front end. So while working in an asynchronous mode of data transfer, to create a buffer, the queues are used. Next application is very important one, handling the interrupts in real-time scenario. For example, you are working in a system and you have pushed a pin drive into it, right? So immediately, whatever you are doing, even you are watching a movie, anything you are doing, you'll get a pop-up window saying that an external device is connected, right? So it can be a threat. So that is more important to give the user an intimation that an external source have entered, right? Has entered the system is very important, right? So than the things which you are doing currently, right? So for that, queues are used. So to handle the interrupt. Next is in real lifetime scenario, there are many things, queues in call centers, many cases you can see. Call forwarding, when you call your friend, if he's already engaged, your call be in the queue, right? So in real life scenarios also, you will see many examples of this. But whenever someone asks you in Viva or in placements point of view, please stick to the applications which are relevant to the concept, that is computer science. Thank you. Next, a next version. As I said, the limitation of linear queue is if the rear is pointing to the highest index, you cannot touch the empty space which is present near the front end. To overcome that, circular queues have come into the picture. What is the beauty of circular queues? Circular queues is they are the a strip-like structure which I have shown is turned into circular fashion. That is, the zeroth index or the first element is going to get attached to the last element. Have a look at this structure. I have attached these two. The total capacity of the queue is 8, where now zeroth element is hooked to the element at index value 7, right? So you can see if in a due course, if I perform few insertions, say 10, 20, 30, 40, 50, they have done 60. Now rear will point. Now 70 if I enqueue. Now my rear point. Now 80 my rear point. Now rear is pointing to the highest index. What if I dequeue few? So 10, 20 and 30 I have dequeued. Then my front is pointing to 40. Very good, right? Now if I try to insert, even though the rear is pointing to the highest index value, as front is not pointing to 0, make rear at 0 and insert the element 90. This is possible. So the major drawback of linear queue, you can overcome it using circular queues. Okay? Yes, sir. So the basic operations that you can perform on a circular queue are the same. Enqueuing, dequeuing, front, rear, is empty or is full. And the applications are basically in case of memory management, process scheduling, traffic signals. Traffic signals you might have seen, you'll get red, orange, and green. And they'll be going first to red to stop, then get cautious, go. Again, stop, get cautious, go. This goes in a circular way, right? So that those are the few applications. Let's look at the working of circular queues. Initially, the queue is empty, and you are trying to enqueue 6. Both front and rear will be incremented. Again, an enqueue, rear will be incremented. You have enqueued 4 elements. Now rear is pointing to the highest index value. And now if I try to enqueue, you have, in case of circular queue, you are going to check 2 conditions. As the front is pointing to 0, as well as the rear is pointing to the highest index, overflow raises. Even if it is one condition is false, you can perform enqueue. Now I dequeue 3 times. See, I have removed 6, 12 and 11. Now my front is pointing to 7. Now if I try to perform the same enqueue operation, as one of the conditions, what were the conditions? If the front is pointing to 0 or rear and rear is pointing to n minus 1, we cannot insert. But now front is not pointing to 0, right? So the 0th index is empty. So just make r is equal to 0 and enqueue operation. Okay, so what if I try to perform 2 more enqueue operation? Simply increment the rate, the normal process, increment the rate, right? Now if you try to increment or enqueue 11, it will be done. Why? Because the front is just a step ahead of a rear. You can see Front is pointing to 3 and rear is pointing to 2. Now, even this is a condition which tells you that the queue is full, overflow condition raised. So, if I conclude, I can say that if front is equal to 0 and rear is equal to n minus 1, this is the one condition, or front is equal to rear plus 1, and if you try to perform enqueue operation, overflow condition arises. Right? So please do remember, in case of circular queues, we have two conditions where you can get overflow. Okay? Right. Insertion operations. So with the help of a piece of pseudo codes, you can check. I have explicitly written these codes for circular queues because they are a bit difficult to understand when compared to linear queues. So if your front is 0 and rear is n minus 1, or front is equal to rear plus 1, is overflow, right? If rear is equal to minus 1, that is, it is empty, then for insertion, increment both or make both of them zeros. Else, you just decrement, if one more condition is that if your rear is n minus 1, then make rear as 0. Or else, the worst case, the normal case, just simply increment the rear and insert. These are the few conditions of insertion. Coming to the deletion. If your front is minus 1, then simply say that it is an underflow, that is circular queue is empty and written. Or else, there can be a case where both the front and rear are pointing to a single element, right? So that means that this is the case where you have only one element in the queue. So what will happen if you remove the only element present in the queue will become empty. So if the queue becomes empty, what should be the positions of front and rear? Minus 1, right? Very good. Else, then one more condition is what if your front is pointing to n minus 1, that is the last position. If it is pointing to the last position, let it point to the 0th index, saying that you have removed the element at the highest index. If these are all not the cases, then simply increment the front and remove the element. See how many cases are there. You can check, you have to first check whether a queue is existing or not by taking the condition front is equal to minus 1. Second is check whether you are having only one element in the queue or not. Check whether the front is pointing to n minus 1 or not, or else a normal case. 4 different cases you have to handle when you are working with circular queues to implement deletion operation. Okay, right. So these are the two simple conditions for is full and is empty, which we have seen just now, guys. Okay, next, the extension of queues, that is double-ended queues. What are these double-ended queues? In linear queue or circular queue, our mindset is fixed that we have to insert an element at the rear end and remove the element from the front end, right? So if we overcome this restriction, saying that we can even remove an element from the rear end and insert an element from the front end, is nothing but double-ended queue. That is, removing these restrictions is nothing but your double-ended queue. So the basic application will be checking whether a given string is palindrome or not. Palindrome is nothing but even when you read from left to right or right to left, it is one and the same. Okay, and these double-ended queues will be an extension of circular queues. So they are most prominently known as circular doubly linked list. Okay, right. They are implemented using circular doubly linked list. So this is a double-ended queue. You can see at the rear end you can perform insertion and deletion. Even from the front end you can perform deletion and insertion. So you will get a bunch of operations: insertion at two ends, deletion at two ends, uh, getting the elements at the rear and the front, and to check whether it is full or empty. So these are the primary operations on a double-ended queue. So let's look at a small animation on the same. Initially, the front and rear are -1s. So when the queue is empty, if you choose either insertion at the front or at the rear, the case is same. You have to insert and you have to increment both front and rear. Okay, right. So now, if you try to insert, my option is to insert an element at the rear. So just increment the rear and insert. Again, in insertion at the rear, increment the rear and insert. Rear, increment and insert. If you try to insert at the front, as the front is pointing to 0 and the highest index is empty, you can make the front point to the highest index value and insert the element. So now, if you try to insert from the front end, decrement the front end and insert. Okay, so now if you try to insert at the if you try to delete a node at the front, so just by incrementing you can do that. Delete at the front end as it is pointing to the maximum index value, make it as 0 by deleting the element at the maximum index. Again, deletion at the rear end, increment, right? So guys, these are few operations: delete at the front, insert at the rear, right? Then delete at the front, right? So again, delete at the front will be incremented. Okay, so insert at the rear, very simple, as it was pointing to the maximum index value and the front is not pointing to 0th index, make the rear point to the 0th index and insert it. So deletion at the rear, as it is pointing to 0, bring it back to max -1. Okay, so that were few operations. So there are two types of dequeues also: input restricted and output restricted. What is input restricted? In input restricted, front end is meant for deletion, right? And it got an extension of insertion. If you revoke that privilege, it is input restricted. Coming to the second one, output restricted, rear end was generally for insertion. An extension operation it got is deletion. If you revoke that operation, it is output restricted. Okay, guys, I hope you understood the basic terminologies in your stacks, queues, circular queues, and double-ended queues and their functionality. Right? I hope you understood this lecture. If you want to go deep into the implementation of stacks using arrays and linked list, queues using arrays and linked list, and the implementation of circular and double-ended queues, you can follow my videos which are posted in our channel. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.